Hello, everyone. Good morning. My name is Mike Rao. I am the pre-sales engineer here at Synera, and today I want to welcome you to the Engineering Workflow Automation and Design for Additive Manufacturing, a technical deep dive. So today I want to cover a few topics. Where do we come from? What do we do? What is our motivation? And also I brought a nice workflow that really highlights how you can use Synera to create design for additive manufacturing components and actually do additional to that, not only the design and the mesh to CAD operation, but also do the costing. That's really important. So let's get started. My name is Mike Rowe. I'm a mechanical engineer, studying in Germany. I have spent my last 10 years of my career in the software industry, in various roles in research, consulting, and software development, as well as sales. And today I'm going to speak about low code. So, what is the problem that we really want to address? And that's something that I really had to experience through pain in my career. When I worked as a young engineer in the FEA department of a company, I learned that a lot of tools are really disconnected, and you have to import and export data from A to B to C. You get data from a customer, different format, then convert it multiple times from step to CAD to answer to a hypermesh into a mesh file, and then you set up your solver decks, run them in HPC, get them back, and use a different tool to do post-processing. So all of those things are really disconnected and they cost a lot of time. And you really need to be an expert to use these tools. So a lot of training is required. And the problem is also that when you work in FEA, for example, you don't really do much CAD work. Neither you do a lot of work with the manufacturing side of things. You really work in silos, and that's really how the industry is set up. So you have a CAD department, you have a department, you have manufacturing where additive is, but all the information that these different departments possess should be shared, right, as a common source of truth. But no, it's siloed and it stays in those silos. So it really all depends on expert knowledge that works sequentially in their silos, and they all rely on their experience. So that is really what I experienced firsthand. People try to overcome these problems by creating island solutions. So either they try to hire people to compensate for the amount of tasks that are on hand. And first of all, they try to automate things themselves, for example, using VBA in Excel or Python with other tools where they can control tools through APIs, or they outsource into cheaper countries. For example, you can outsource FEA work to India or to any other country in the world where labor costs are much cheaper. And people use scripts that are really available across tools. So there are a lot of approaches to the problem, but none of it is really the solution to a problem. So in the perfect world, automation happens on a much broader level. Engineers would be able to connect disciplines, they would share knowledge, and they wouldn't be trapped in silos. So this is the motivation of Synera. And Synera is a really innovative startup that has been founded in 2018, funded through venture capitalists. As you can see, a lot of OEMs already using our platform. And we had one motivation. We wanted to revolutionize the way how engineers work. We want to automate these repetitive, autonomous tasks. And our approach to the problem is using low-code language. And what is low-code, you're asking now? So low-code is pretty much a form of visual programming. And why we say visual? Because visual programming is much easier for engineers to, rather than using Python or C# where you do really code things. So in order to show you what low code is, I have created a demo file for you. And you maybe have seen in the previous demo the basics of Synera. Today we're going to have a deep dive and we're going to look at the design. And this is this GA engine bracket that we want to convert into an additive design. And from there, we also want to do a cost optimization because we want to find out what's the best build orientation of the part. So now you look at the part and you see that in the first place, I have actually imported geometry. But what did I do? I imported a step file. And then you would say, well, it's just a dumb part. I'm losing all the parametric entities the part came with. So what happens if I just want to change the bolt location? Well, you could do that. So with our functionality to remotely control external CAD programs, you can actually connect a native CAD file, and in our case, that could be an X, and bring in all the parameters from an NX part into Synera. So it means you do not convert, you actually connect. So you control your CAD program remotely. And we can do that with any other CAD tool like SolidWorks or CATIA. We can just type in any run NX run node that we want to use. So this is a really benefit of low code, that you are really flexible here. And if your requirements change, the CAD software changes, then you use a different node. So let's come back to the workflow. So our aim is to import this design space, pretty much the original bracket, and convert it into an additive bracket. And therefore, we have color-coded the surface. So this is a viewer panel. If I double-click in it, I can actually zoom in it and rotate and pan. So as you can see, I've color-coded the constraint surface in green and load surfaces in blue. And I did that because we can actually extract these surface colors in Synera and create new bodies or apply bounding conditions to the colors. So in the next step, we actually have extracted the color codes and created these non-design and design spaces. So the design space, so the topology region, is yellow, and the non-design space, the mounting points, that's the geometry that we want to keep later, is green. And here we go to the next stage where we transfer all that data, the design space and non-design space data, into our hexagon emendate nodes. So these are modules that we're using. Modules in the sense this is third-party technology hosted on a Synera platform. On the other hand, we also have connectors, and that, for example, is an OptiStruct connector. And we can just type it here. OptiStruct optimized. This is a connector that actually requires you to have OptiStruct installed on your computer. So once you have OptiStruct installed on your computer and you're using it, you could also connect it to Synera and then control OptiStruct from Synera. But in our case, we decided to use the hexagon nodes, which provide a level set topology optimization technology. So with these nodes, we can define the design space, the non-design space that are highlighted here in reddish and gray. And in the next step, we have actually set up our boundary conditions, load cases, and created our FEA model. And this is the model that we would want to run in the topology optimization algorithm. So once the node ran, sorry, that was the wrong one. Once the node ran, we would convert it. But here's a question from the audience. Someone asked if we could actually use a different solver technology. And I say, yes, we can. So in our case, we could also bring in HyperWorks Solid Mesh node and run the OptiStruct FEA solver. So this is possible. So instead of using hexagon. So once we have the CAD result, FEA results, we can convert the mesh that you can see here into a quad mesh. And from there, we convert the quad mesh into a CAD body. Of course, the last operation is the Boolean intersection between the original mounting points and the topology optimized body. But now we're not at the end. We really want to know what is the most efficient, or what's the most cost-efficient build. So we know the density of our part, we know the geometry of our part, but we don't know what's the cost and how many parts we could fit onto the machine. So therefore, we have actually built a casting and nesting node. And I know this looks like spaghetti now, but it is quite simple. So on the left-hand side, we're actually converting our body into a mesh. And as you can see when you hover over it, our mesh has 75,000 vertices and about 146,000 faces. So this is a simplified body that we can bring into this LBM casting node. And in this casting node, we can actually use different orientations. So we highlighted these sliders in purple because we use them as parameters. So what is a parameter? A parameter is a value that you can control in the design optimization cycle. So any slider that you can see here in Synera can be converted into a parameter. And the parameter setup that you can see on the bottom here shows you all the parameters that you can use in the design of experiment study. And when we talk about parameters, we also have to talk about responses. Because every design of experiment study or optimization has parameters to change, and that has responses. And in our case, the cost of the part that will be computed from that node is a response, as well as the number of parts that fit onto a build plate. The build plate is defined here. We just use a standard build plate of about 400 by 400 millimeter. It's a reasonable sized additive machine. And our objective is mentioned here. We want to reduce the cost. So in order to achieve that, we have actually set a parameter study and ran the design of experiments. What is an exploration of the design space? So we just created 10 different studies, and they all come in with different cost responses and different quantities per build plate. And now we can actually bring that into an optimization loop, and the optimization can run for a while and find the cheapest or the best or the most cost-efficient design. So when we bring in the graph that we created, let me highlight that here, you can actually see that we created a nice Pareto front, and that shows you that the most cost-efficient design is the design down here for about 130 euros per part, and with a maximum of parts of about 18 parts per build plate. That's the most cost-efficient design. All the other designs are just design options. So I hope this was helpful and it gave you an overview of what's possible with Synera. Please join us in the next session for our low-code lab on February 29th and our new release March 6th. So feel free to scan the QR code, sign up, or download the latest version of our release. And yes, I'm happy to see you next time. And thank you. All the best. Bye.